Hello and welcome. Today I'm going to share to you three types of reactions of benzene and its compound. Let me embark from this alkylation of benzene. So it is actually known as a Friedel-Crafts reaction. It is actually the reactions between benzene with chloroalkanes in the presence of anhydrous aluminum chloride to give alkyl benzene. So it's actually benzene. Okay, for example, I have benzene here, and then I have a chloroalkane. So for example, alkane means that you have a saturated hydrocarbon. For example, I have C2H5Cl here, and then in the presence of AlCl3, and the condition is actually dry. All right, so how do we get the product for this reaction? So again, if you remember in the previous tutorial, right? So benzene always avoid the addition reaction. So benzene favors, or likewise, benzene favors the substitution reaction. All right. So if you see here in chloroalkane, we have two dipoles. We have two poles, which is the Cl, which is negative, and while the other one is actually positive. All right. So if you know this one already, then it will guide you on how you can actually predict the product. All right, so we have a benzene. All right, so we have a benzene. Sorry, excuse me. We have benzene, and then we have also dipole positive of ethyl. All right, and then um, the mechanism is actually electrophilic substitution. Right, so benzene plus C2H5. So in this case, C2H5 is actually the electrophile. So this is actually electrophile, means that philia means love, electro means negative. So why C2H5 plus is electrophile? Because it has a positive side, right? So one of the pi bonding system inside the benzene ring will pick C2H5. Then this reaction is happen at slow rate. All right. Now you have the intermediate of this one. All right. And then you have H. All right. Now, why I draw this? Because the electron is used to introduce C2H5. All right, and then next thing is actually always remember that benzene tries to restore the resonance system. All right, so meaning the electron, all right, the electron in hydrogen is delocalized to benzene ring. Then you'll have this final product of C2H5. So you'll have C2H5. All right, so now you have a alkyl. So this is actually alkyl and it's benzene. So name for this one is, ethyl benzene. So it's actually alkyl and then it's actually benzene. All right, and then we have Cl minus here. So Cl minus will get H and then it becomes HCl. Right, so the product for alkylation of benzene is actually alkyl benzene. All right, so you have in this case you have C2H5Cl, C2H5 benzene and hydrochloric acid. All right, next is oxidation site. All right, so we have an oxidation site of chain on arene. All right, so basically you can actually oxidize any possible methyl or alkyl that you have in the benzene ring. All right, so then you'll have carboxylic acid. All right, Now, for example, I have a methyl benzene. All right, so for example, methyl benzene. So this is actually methyl, right? And then if I use K-4, if I add K-4 in the presence of H plus, all right, then I can get the species, all right? So this is actually benzoic acid, all right? For example, I have another one. I have a, let's say I have this one, CH2OH. And then if I add oxidizing agent of a K-4 in the presence of OH minus, then I shall have benzene, and then I will also have a COOH. Remember, you have a alcoholic K-4, therefore one of this one is actually becomes CO2, right? So because if you have a CO2, so CH2, it becomes CO2 because you use strong oxidizing agent to convert H become O. So, and then the other one is actually 2 molecules of water, right? So when you have this alcohol, all right, and then you add K-4, then one of those CH2 becomes CO2 as the product, and the other one is actually water. All right, how about I have for example, I have another type of benzene. For example, I have a CH2 COH. If I add K-4 in the presence of a OH minus, then what's the product? So you don't need to worry and afraid of this one, because basically as long as you have H, you can actually convert it to CO2. Okay, so you'll still have a same you still have a same benzoic acid, but you definitely oxidize CH2 becomes CO2. So you have COOH and then CO2. The CO2 comes from the CH2, all right, and then another one is actually water. Okay, so don't be confused when you are dealing with this kind of reaction. All right, so another one is actually phenol. Okay, so another one is actually phenol. How about phenol? So phenol, basically you have a benzene ring with OH attached in one of the carbon in benzene ring. All right, so basically you can show the reactions is using carboxylic acid. Okay, so for example, let me begin with this one. You have a phenol. By the way, the physical state of phenol is actually white solid. Okay, so it is actually white solid. This is actually one of the most questions that we have in the past paper. So for example, if we add phenol, all right, so which is reactions with alcohol, all right, so it will give you this reaction. So actually this is actually equilibrium. Let me fix this one. Actually this one is at equilibrium, goes there, and goes there. So it will give you O minus aqueous plus water, liquid, right? So conditions for this reaction is actually aqueous sodium hydroxide at room temperature, right? At room temperature. So in this case, phenol, right? Phenol is actually, or phenol behaves as acid because it donates proton. All right, so if you can see here, O is more electronegative than H. So this one is delta negative, this one delta positive. The electron goes to O, then you'll have this one. Okay, so this is actually proton donor. So proton donor is actually acid. So it's actually acidic acid. Okay, so that's the first reaction between phenol that behaves as acid with sodium hydroxide, which is base, so becomes salt and water. So it's actually reactions between acid and base to give salt and water. All right. So the other possible reactions between phenol, okay, that include phenol is actually the phenol with bromine water to give uh, 3 substitution of bromine in benzene ring of phenol. Okay, so for example, you have a phenol again. Okay, and then the phase of phenol is actually aqueous plus 3Br2. Sorry, you might not see this one. I'll fix it. So 3Br2 aqueous to give. All right, so this is the thing, because you have quite a number of bromine in the form of aqueous, then it will be attached in carbon number 2, 4, and 6. The details why 2, 4, and 6 is actually because the phenol is actually ortho and para director. So ortho and para director will be discussed in the other video. All right, so you have a BR, and then you have a 3HBr. How do I get 3HBr? Because one H that's substituted by Br is 3, so total is actually 3, and then you have a 6Br here. So you already enter 3Br, and the other Br will join with 3H to give 3HBr. Okay, where's the 3H is actually from number 1. You have actually H here, right? H and then H. So this H will join in with the remaining 3Br. Okay, so you'll have this one. Okay, so reactions type is actually substitution. So this is actually substitution reaction, and of course you have a condition is actually bromine, water. Okay, and no catalyst needed, and then mechanisms actually electrophilic, right? Okay, now I have another reaction of phenol. It's actually phenol. It is actually possible to react with phenol. All right, reacts with acid chloride. So CH3COCl. So this is acid, and this is actually chloride. So this one is actually negative, and the other one is actually positive. Again, you have a O is actually negative, and H is actually positive. So O will pick this group, and then Cl will pick this H. Now you have a substitution reaction. All right, so you have a 1, 2, and then you have a CO. Okay, excuse me. So you have a O here, and then you have a C double bond, and then you have CH3. Okay, and then you have HCl. So this one, H and Cl together. Okay, so conditions for this reaction, it is actually you must write aqueous sodium hydroxide. Okay, aqueous sodium hydroxide. Aqueous. Okay. All right. That's all from me. Thank you for watching, and I hope you enjoyed the video. Thank you.